Hello, everybody. We're on to lesson 4.4 on perpendicular lines, and this lesson starts with two constructions. And so we'll take a look at the first one is a review. It's a construction that we did do maybe a couple weeks ago, and that is constructing a perpendicular bisector. So we've done that before. This is just going to be a quick review for you. So if we have a segment AB and we want to construct the perpendicular bisector, you might remember that the steps go like this. You put the compass point at A or at one of the endpoints, open up the compass so it's clearly past halfway, make an arc, and then move the compass to the other point, and with the same compass setting, make another arc. And then where those two arcs intersect, we can draw a line. And that line L is the perpendicular bisector of AB. Okay, so go ahead and practice it one more time. Make a segment on your paper. Maybe this time we'll call it PQ. And see if you remember the steps to construct a perpendicular bisector of PQ. Pause your video and press play when you're done. Okay, so when you do the perpendicular bisector of PQ, you put the compass point at P, open up the compass so it's definitely past halfway. Make an arc from P. Make the same arc from Q. And where those two arcs intersect, we'll draw a line through those intersection points. And now, let's see, we'll call it line K. Line K is the perpendicular bisector of PQ, meaning it cuts PQ exactly in half, and it's forming a right angle as well. Okay, the second construction is creating a perpendicular from a point that's not on a line. So if we have line L and a point P down here that's not on L, we want to construct a line through P and perpendicular to L. Okay, and so the steps go like this. Put the compass at P and open the compass up so that it reaches a little bit past line L. Make an arc. So those 2 points where the arc intersects line L, we'll call those A and B. And now what we want to do is repeat the construction that we did up here, which is the perpendicular bisector of AB. So we're going to put the compass at A, make sure it reaches past halfway. Make an arc from A. Make the same arc from B. And now if we draw a line connecting these 2 points, it should also pass right through point P. And so there is a line that passes through P and is perpendicular to L. Okay, so this time draw another line, and we'll put point P here. Okay, so go ahead and see if you can construct a line that goes through L and is perpendicular to line K. All right, so we put the compass at P, and then we need to open it up so that it extends beyond the line, so that we can make an arc from P that crosses the line twice. We're calling those 2 points A and B. And now we construct the perpendicular bisector of AB. So if I put the compass at A, open it up at least halfway, past halfway, make the arc from A and from B. Now if I draw a line passing through those 2 intersection points, it should also pass right through P, and it looks like it does. It goes through P, and it's perpendicular to line K. Okay, now one thing that we should notice on all these perpendicular lines that we just constructed, if we pick any point, any random point on the perpendicular line, and draw segments to the endpoints, A and B, what we should recognize is that those are always going to be the same length. So if I put my compass here, it reaches and adjust it so it reaches just to that point. Okay, that's the length of that segment. This segment will be exactly the same. Okay, it's true for any point that you pick. I'll pick a point up here this time. If I draw the segments from that point to the endpoints A and B, adjust my compass to measure this distance, notice that it's exactly the same as that distance. Okay, so these 2 segments were the same. Now we see that these 2 segments are the same. I can pick a point anywhere on the perpendicular line. It doesn't really matter where it is. I'll take this point, for example. Anywhere I go on the perpendicular, the distance to the 2 endpoints is the same. So this segment is the same length as this segment. Okay, that will happen on any of these diagrams that we created. If we pick a point on the perpendicular line, any random point, and draw segments to the endpoints of the original segment, that length and that length will always be the same. So you can test that out on your own drawings. You can do the measurements with your compass or with a ruler, and you'll see that that is always the case. Okay, so that leads to the first theorem in our book, which is on page 196, or the first theorem in this section anyway. So what we just saw is written up in this theorem, the Perpendicular Bisector Theorem. Okay, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, so again, that's saying if we have a segment like AB and we have a perpendicular bisector, any random point I pick on the perpendicular bisector will be equidistant from A and B. So that means that distance to A and that distance to B will always be the same. Pick another random point. That point is equidistant from B and A. Okay, so that's what the perpendicular bisector theorem is saying. Any point that you pick on the perpendicular bisector is going to be equidistant from the endpoints. And then on the next page, we have the converse of the perpendicular bisector theorem. So the converse means it reads in the opposite direction. So the first theorem says if A, then B. The converse would be if B, then A. So in the perpendicular bisector theorem, we said if we pick a point on the perpendicular bisector, then it will be equidistant from the endpoints. This is saying the opposite. This is saying that if a point is equidistant from the endpoints, then it lies on the perpendicular bisector. So it's the same statement as we saw in the perpendicular bisector theorem, except the hypothesis and the conclusion switch places. So that's what it means to be a converse. And so what this is saying is that if you have a segment and you pick any point that is equidistant from the two endpoints, that point, in this case P, must be on the perpendicular bisector of AB. And if you do it again, if you find another point that happens to be equidistant from the endpoints, that is on the perpendicular bisector also. So if you have two of those points, you can connect them, and that gives you your perpendicular bisector. Okay, and so that is perpendicular and cuts segment AB in half. All right, so that is the converse of the perpendicular bisector theorem. So converses aren't always true, even if the original statement's true. It's not always true if we read the statement the other way. For example, if I said, if it rains, then my car will get wet. That's a true statement because my car's outside. If it rains, it's going to get wet. But it's not true the other way around if we say, if my car gets wet, then it rained. That's not necessarily true because my car could have gotten wet by somebody spraying it with a hose, or the sprinklers got it wet, or something like that. So even though the original statement is true, taking the converse is not always true. In this case of the perpendicular bisector theorem, both the original statement and the converse are true. Okay, so let's go ahead and go to problem 7. Pause your video and see if you can find the length of AC based on one of the two theorems that we just saw. So if AD is 10, then DC is 10 as well, and BD is 6 inches. And so now if we use the Pythagorean theorem, we can find the length of AC, or we can find the length of AB and BC. So if I call this length x, then by the Pythagorean theorem, x squared plus 6 squared equals 10 squared. So x equals 100 minus 36, which is, or x squared is equal to 64. So x equals 8. And since that's 8, then that has to be 8. And the reason why we know that is because if these two are equidistant, then it must be on the perpendicular bisector. And so now we can see that AC is 16. Let's actually go back to the top of page 197. Okay, and go ahead and try problems 4 and 5. Pause your video and press play when you're done. So ED is 16, DA is 20, find DC. So since we can see that BD is a perpendicular bisector, there's a right angle, and these two lengths are the same, it must be a perpendicular bisector. And so the perpendicular bisector, any point is going to be equidistant from the endpoints. So if DA is 20, then DC is also going to be 20. And then we can use the Pythagorean theorem. So that answers that question, that DC is 20. And then for number 5, if EC is 15, and BA is 25, find BC. So if this is 25, then this has to be 25 because it's on a perpendicular bisector. So BC is 25. Okay, and then we'll finish up with problem 9. We're given that we have two pairs of parallel lines. B and D are parallel, and lines C and line E are also parallel. So use that information and see if you can find the measure of angle 4. Pause your video and try that out. All right, so if we label angle 1 as 50 degrees, we know that B and D are parallel. We also know that C and E are parallel. So we can mark those parallel. And so from what we learned in the previous couple of sections, if the lines are parallel, then corresponding angles are congruent. So 1 and 2 are corresponding, so 2 would be 50. And we know that angle 5 is 90. So if that's 90, then that means that is a right angle, that is a right angle, that's a right angle all the way around. And so 2 and 6 together add up to 90. So that means angle 6 must be 40. And angle 4 is a vertical angle to 6. So if 6 is 40, then angle 4 has to be 40 also. And that's it for today's lesson. Have a great day.